We're going to start our discussion of electric potential first by forming an analogy between electrostatic and gravitational forces. So let's review what we know about gravitational force. Gravitational force appears between two masses M1 and M2. It's an attractive force. It's equal to universal gravitational constant G multiplied by the product of the masses M1 and M2 divided by the distance between them R squared. And it's a conservative force, so it's derivable from a potential energy. In comparison, the electrostatic force is 1 over 4 pi epsilon 0. Epsilon 0 is permittivity of free space. The product of the two charges, Q1, Q2, divided by the distance between them squared, R squared, and electrostatic force is also a conservative force. Now, regarding the force constants, the universal gravitational constant G has a value 6.67 times 10 to minus 11 Newton meters square over kilogram squared. The Coulomb constant K, which is 1 over 4 pi epsilon 0, is approximately 9 times 10 to the power 9 Newton meters square over Coulomb square. Now you can see that there is a big difference between these force constants. The direction of the force for the two masses M1 and M2, the gravitational force between them is always attractive. For two charges Q1 and Q2, whether the force is attractive or repulsive depends on the sign of the charges. For opposite signs, it's attractive. For the charges with the same sign, it's a repulsive force. If you look at the order of magnitude of the gravitational force versus electrostatic force, let's take two masses M1 and M2 1 kilograms. The distance between them is 1 meters. The gravitational force is the gravitational constant, 6.67 10 to minus 11 newtons. This is a very small force. It's only significant for very massive objects. If I take two charges, Q1 equals Q2 equals 1 coulomb, the distance between them is 1 meters, then the electrostatic force I would find to be 9 times 10 to 9 newtons. In general, this is much stronger than the gravitational force for charged objects. So let's take a look at an example to basically clarify this point here. Compare the gravitational force and electrostatic force for two electrons at a separation of 1 nanometers at rest. Now, the gravitational force between two electrons at rest is the gravitational constant 6.67 times 10 to minus 11. Then we have the mass of rest mass of the electron, 9.11 times 10 to minus 31 kilograms squared. The distance between the two electrons is 1 nanometers, 1 times 10 to minus 9 meters squared. And this gives us a force of 5.5 times 10 to minus 53 newtons. And it's an attractive force. Now, if I calculate the electrostatic force between these two electrons, because the electrons have both negative charge, it's going to be repulsive. The Coulomb constant, 9 times 10 to 9, the charge of an electron squared, which is 1.6 10 to minus 19 coulombs squared, divided by the distance, 1 times 10 to minus 9 meters squared. The force is 2.3 times 10 to minus 10 newtons. Now you can see that for two electrons at a separation of 1 nanometers at rest, the order of magnitude of the electrostatic force is much, much greater than the gravitational force. Now the concept of field for the interpretation of forces by using action at a distance principle, the gravitational field G is the gravitational force per unit mass, test mass m0, it's in newtons per kilograms. Electric field is electrostatic force Fe divided by the charge Q0. So this is the force acting on a test charge, newtons per coulombs. So we have the same picture in both electrostatic and gravitational cases. The potential energy associated with this force, if I go from point A to point B, the change in the potential energy, delta U, is minus the integral, path integral from A to B, the gravitational force dot product with ds. So it's minus the work done by the gravitational force, because the gravitational force is minus the gradient of the potential energy. It's a conservative force. So this is the force given in terms of potential energy. This is the potential energy given in terms of the work done by the force. The same principle applies to electrostatic case. The change in the potential energy is minus the integral A to B, electrostatic force dot product with ds, and Fe is also derivable from this potential energy minus gradient of U. It's a conservative force. So since both forces are conservative, the work done by these forces is independent of the path taken. So it doesn't matter how I go from A to B. I can go directly, I can follow some other path, sinusoidal path, etc. It doesn't matter, because it only depends on the endpoints, the energy at these two endpoints. Okay, now let's consider the following problem. What is the work done by the gravitational force for the case when a mass m is taken from point A towards point B? And I can take this from point A to point B along the blue path or the red path. And here's my x-axis, here's my y-axis. The distance between point A and point B on the y-axis is h. That's the height. Okay, so what is the work done by the gravitational force? It's integral from A to B, gravitational force dot product with the displacement ds from A to B. The gravitational force is mass times the gravitational acceleration or gravitational field g, and it's going to be pointing in minus j hat direction. It's pointing downward. Dot product with ds. Now, since the gravitational force is independent of the path taken, it doesn't matter which path I take, so I can just basically go from point A to point B on the y-axis. On the x-axis, because the force does not have an x component here, there will be no contribution. So this can be written as minus mg j hat dot product with integral A to B ds, and this is minus mg j hat dot product with hj hat. So that's the delta s is basically this delta y. So you can see here delta s is equal to delta y in this basically example. The contribution from delta x is 0 because the force is on the y-axis. So let's say that this is delta r is equal to delta y. This has turned into dr on the y-axis because the delta s actually includes a delta xi hat plus delta yj hat, but there is no contribution from delta x. So the actual displacement that makes a contribution is delta y, which is hj hat. Okay, so you can see that the answer here is minus mgh. So what I find is that minus mgh is equal to the work done by this gravitational force. The work done by the gravitational force is minus the change in potential energy. So minus delta U is integral A to B FG ds. So this is minus the change in potential energy, UB minus UA, minus delta U. And you can see that the potential energy at point H, at B, so let's basically write this as UA minus UB. So I can define the potential energy to be, let's say, as my reference point, the potential energy here is 0. So this goes away, and I find that the potential energy at point B is, potential energy at the height h is mgh. Okay, so this is basically utilizing the work potential energy theorem. It comes from the definition of the conservative force. The work done by internal forces is basically minus the change in the potential energy. What is the work done by the electrostatic force for the case when a charge minus q is brought from point A to point B in a uniform electric field E, which is pointing from B to A? Okay, so work done by the electrostatic force, integral A to B Fe dot dr. This is the integral from A to B. Now, what is the force acting on this charge? Because this is minus Q and the electric field is pointing towards it, basically this electric field tells us that there is a positive charge distribution here and negative charge distribution here. So this is basically going to give us a force that's pointing from point A towards point B. So this force is Q E, magnitude of the electric field, in r hat direction. Now our displacement is in r hat direction, dr r hat. So we find this is integral A to B QE dr. So basically here we have noted the electrical force here is Q minus Q times the electric field, which is minus Q magnitude E in minus r hat direction. So this is QE in r hat direction. Okay. Now what is the work done by the electric field? It is QE r evaluated between A and B. So if I set the position of A to be 0, this is QE position of B minus QE position of A. That is minus the change in potential energy minus UB minus UA. So this is UA minus UB. So if I set the potential energy reference at A to be 0 and the position A to be 0, then I find that the potential energy at point B would be minus QE R. Okay, so RB, but because RB minus RA is 0, this would be equal to minus QER for this example. Okay, so here what I have done is I set the potential at a certain point to be 0 because potential energy is only meaningful if in the relative scale, but in conventionally we set the potential energy to be 0 at infinities, and that's what I'm going to consider next. Now, before I do that, the concept of potential is basically potential energy per unit mass, m0. It's basically mgh divided by m, that's g times h, that would be the potential at that point, and u over q0, the potential energy per test mass, It's basically kq over r. That's the potential energy per unit charge. Okay. Now, as I said, both potential and potential energy are meaningful in relative scale. So conventionally, we consider zero potential energy not at a point like this. We take it to be zero when the objects are at rest at infinite separation. So for the gravitational case, if I bring a mass m from r equals infinity to a finite distance r to be closer to another mass m, let's calculate the work done in going from infinity to r. Okay, so this is the integral from infinity to r gravitational force Fg dot ds. So I'm calculating the work done by the gravitational force, not by an external agent. So since this is basically r, this is infinite, r hat is pointing in this direction, and my mass is basically being brought towards the mass m. Okay, so this is going to have a value integral infinity to r. The gravitational force between the two masses is gravitational constant g, m1, m2, which is m square, divided by r square, and it's an attractive force, so it's pointing in minus r hat direction. This is going to be a dot product with dr in r hat direction. Why? Because here the dr value will be negative. So I'm going from infinity to r. So this would dr times r hat, which is my dr vector, is actually negative. Okay, so this would be in the direction of the of travel here. So let's get rid of this. Basically, dr vector is dr r hat, and dr will have a negative value when I approach this mass. Okay, so this is going to have integral from infinity to r minus g m square over r square dr, and that integral will give me g m square over r square, m square over r, because the gm square over r with a minus sign will be this integral, evaluated between infinity and r. So I find that the work done by the gravitational force going from infinity to r is g m square over r, and this is equal to minus the change in the potential energy, so that is minus the potential energy at r minus the potential energy at infinity. The potential energy at infinity minus potential energy at r, this I set to 0 by convention. That's my reference point. So I find that the potential energy at r is then minus g m square over r. Why is it negative? Because this is a attractive case, so we're basically moving in the direction that is making the masses come closer. Therefore, this is going to cause a decrease in the potential energy. So the system energy is reduced. The system energy is reduced as the masses approach. Now, if I consider a similar situation for electrostatics, I have charge minus q stationary here. I'm bringing a charge plus q from infinity to a distance r with respect to this minus charge minus q here. Okay, so work done by the electrostatic force going from infinity to r as the internal force is integral infinity to r electrostatic force dot dr. This is again the integral from infinity to r. What is the direction of the electrostatic force here? Well, this force acting on plus q is basically directed towards minus q, so that it's in minus r hat direction. The force is kq squared over r squared in minus r hat direction, and this is dot product with dr r hat, and dr itself will be negative as I approach here, so dr vector basically will be pointing in this direction. Why? Because you can see that r hat is pointing in this direction, dr will be negative, so dr vector will be pointing in this direction. And this integral will give me kq square over r evaluated between infinity and r. So work done by the electrostatic force going from infinity to position r will be minus the change in potential energy minus u at r minus u at infinity. And once again, I set the potential energy at infinite separation for two charges at rest to be 0. So that's my reference point here. So this is 0. And this gives me minus u of r equal to k q square divided by r. You can see this is going to be kq square over r minus kq square over infinity, which is 0. So this will be kq square over r, and therefore I find the potential energy at a separation r for two charges plus q minus q to be minus k q squared over r. Okay, so once again, I see that the system energy is reduced as the charges approach each other. Okay, so let's summarize what we said here. We have compared gravitational and electrostatic cases. Gravitational force, G m1 m2 over r squared. Electrostatic force, Coulomb's constant, K, 1 over 4 pi epsilon 0, Q1, Q2 over r squared. Both forces conservative, but the force constants have a big difference. The gravitational constant is 6.67 10 to minus 11. Coulomb constant is 9 times 10 to 9 in SI units. The gravitational force is always attractive. Electrostatic force is attractive for charges with opposite signs, repulsive for charges with the same sign. And if we compare the order of magnitudes here for two electrons at 1 nanometer at rest, we see that electrostatic force is far greater than the gravitational force. The gravitational field is gravitational force per unit mass. Electric field is electrical force per unit charge, Q0. The potential energy force relationship is the same for the two cases because they are both conservative forces. The forces are derivable from a potential energy as minus gradient of potential energy. The change in potential energy is minus the work done by the force. That's work potential energy theorem. We have looked at two examples. If I take a mass from point A to point B, setting the potential energy to be 0 at point A, I find that the potential energy at point B is mgh. If I do the same exercise for a charge minus q that is moving in a uniform electric field E, pointing from point B towards point A, if I set the potential energy to be 0 at point A, I find a similar result. At B, the potential energy is minus q ER, because my charge sign is minus here. This is minus q ER. So M is replaced by minus Q, G is replaced by E, H is replaced by R. So there's complete analogy between the two. The potential is defined as potential energy per mass and potential energy per charge in the electrostatic case. It's G times H or KQ over R, or we can write this as GM over R. And they're both meaningful in relative scale, and I have shown that when I change my reference point from point A to a point at infinity, the potential energy at a distance r for two masses is minus gm square over r. Now you can see that the potential will be minus gm over r here. And for the electrostatic case, it's going to be minus kq square over r for the attractive case. And in the case of attractive scenario, we have a negative potential energy at a separation r here, because the system energy is reduced as the masses or the charges with the opposite sign approach each other.